Welcome back, students, to another one of my videos produced for the New South Wales Higher School Certificate Physics course. Today we're investigating the motor effect. This covers syllabus topic 6.2 of the New South Wales Physics syllabus. The inquiry question is, under what circumstances is a force produced on a current carrying conductor in a magnetic field? And some of the detail points state students will investigate under which conditions the maximum force on the conductor is produced. Students will investigate the relationship between the directions of the force, the magnetic field strength and the current. And students will investigate conditions under which no force is produced on the conductor. Now today I'm going to look at just two of those points. We're going to look at the conditions to produce the maximum force and the relationship between the directions of the force, the magnetic field and the current. For this we need a current carrying conductor and a hopefully uniform magnetic field. Today I'm going to produce the magnetic field using two permanent magnets. They are ceramic or ferrite magnets, quite strong, and these two magnets have their north and south poles on their flat parallel faces, so they stick together like that. If I reverse one of them, they produce repulsion force and I can't bring them together. I'm going to need some iron poles, which I'm making from these soft iron brackets, to produce a magnetic gap. So I'm going to place one of the permanent magnets on one side of the gap and the other one with its north face facing the south pole on the other side of the gap. So I have a uniform gap between these two permanent magnets. Now there is a challenge involved in measuring the force on a conductor. I have a conductor here, which is actually not one conductor but three. I've taken some 0.5 millimeter diameter copper wire and made it into a loop 3 times, so that in fact the conductor will go through the magnetic gap 3 times. When the current passes through, it will go around the loop once, then around the loop again, and then out, so that the segment that's placed within the magnetic gap will actually have 3 conductors side by side, with the current going in the same direction. The reason for doing that is to make the experiment more sensitive. It will triple the force experienced on the conductor. Now it's a little bit difficult to measure the force on a conductor if I allow the conductor to be suspended by something like a scale. It's actually far easier if I suspend the magnetic structure on a scale and measure the difference in the force on the magnets. It makes no difference because according to Newton's third law of action and reaction, if there is a force produced on the conductor in one direction, then there will be a force on the magnetic field in the other direction. So I can measure either the force on the conductor or the force on the magnet, and they should be the same. So I choose to measure the force on the magnet, and for that I have a very sensitive digital scale here which measures to 1/100th of a gram. Now it's a little bit difficult for me to show you the readings that are going to appear on the scale here, because I have to keep this scale horizontal at all times, and the camera will be filming at an angle, so you won't be able to see the values and I'll have to read them out to you. So to get started, we have to place the force measuring device absolutely horizontal. The magnet structure must go onto it, also staying horizontal, and then I have to suspend the conductor, so I'll need a third hand, and I have my third hand here which will help me to suspend the conductor within the magnetic gap. And I want the conductor to be parallel to the gap and in the center of the magnets, so it's in the position of uniform magnetic field, which I've done. Now I need to lower that a little bit. Alright, I'm happy with that. So I have my conductor now passing through the magnetic field, immersed in the region of uniform magnetic field. So the magnetic field is going out of the page towards you. The current is going to be going from right to left, and the source of the current will be this laboratory precision DC power supply. And I can set the value of the current to any value I like. So I don't know the magnetic field strength, but I do know the value of the current. So ultimately we should be able to calculate the strength of our magnetic field. For this we're going to need a table for recording data. So I've already prepared a suitable table of 3 columns. The current in amperes is going to be measured in this column. The change in mass in grams will be in this column, and I'll convert that to a change of force in this column. Okay, so let's get started. We need to connect the positive terminal of the current supply to one side of the conductor, connect the negative terminal to the other side of the conductor, and get ready to record results. I'll call out the values and I'll record them in my table of data. Turn on the scale. The scale has already tared, that is, subtracted the mass of the magnet structure, so the scale is already reading 0.00 grams at 0 current. So I'm going to turn the current down on my laboratory power supply, turn it on, and confirm that I have 0 current, and the digital scale is also measuring 0.00 grams. So I'll record that value to 2 significant figures. Now I'm going to turn it up to 0.5 of an amp. .50 amps, and I'm recording an increase in mass on the magnet of 1.03 grams. 1.03 increase in mass. In other words, the force on the conductor is pushing down on the magnet structure and pushing up on the copper wires. So the forces are equal but opposite. Now I'll increase my current to 1.0 amps. There we have it. Force registered on the scale is now 2.02 grams. Increase plus 1.0 amps. I'm going to jump to 2.0 amps now. And the force change on the digital scale .07 grams plus 2.0 amps. Now when current values start getting up quite high, this is capable of producing a heating effect in the copper conductor. So I want to keep touching the copper conductor with my fingers to see whether I'm getting any significant heating effect. I don't want to actually burn the wires. So I'll do these final couple of values rather quickly so I don't build up too much heat in the wire. So let's go to 3.0 amps. .00. Force registered on the scale is 6.00 grams plus. Go to 4 amps. The force on the scale is 7.99 grams plus. How's the wire going? Oh yes, it's starting to get noticeably warmer. Now we'll go to 5 amps, and that's the limit for this particular laboratory power supply. I don't normally go higher than that. And the force measured on the scale is 9.88 grams. Okay, off. So we've got our table of data now, and our job now is to graph the data and see if we've got a linear relationship between the change in mass on the scale and the current through the conductor. So, having graphed the results, I can show you now the nature of the relationship between the force experienced on the scale and the current passing through the conductor. And as you can see, it's quite a linear relationship. So we have change of mass recorded on the digital scale versus current on the horizontal axis. And I've also added on the other side of the vertical axis the force in newtons that this change of mass would represent, because we need that value in newtons to plug into the motor effect equation. So the critical thing about this graph is the slope of the line. The slope of the line is proportional to the strength of the B field in Teslas. So we need to calculate that slope, which I've done here through the usual form of rise over run, taking 2 data points on the graph, and the slope comes to be 0.0194. That's to 3 significant digits. Now we need to look at the equation of the motor effect. So the equation of the motor effect says that the force per unit length, F over L, is equal to the product of the current times the strength of the B field and sine theta, where theta is the angle between the conductor and the B field. In this experiment, we made the angle 90 degrees. Now I've also added in here little n because we made the conductor go through the magnetic field 3 times by forming it into a loop. So n will be 3. So plugging in that data, the theta is 90 degrees, sine of theta is 1. The length of the conductor that is immersed in the magnetic field I measured as 0.046 in meters. So all these are SI units. The number of turns of the coil going through the magnetic field was 3. So you plug that into the equation of the slope. N times B times L times sine theta is equal to the value we calculated, 0.0194. So working it backwards, we've derived now the strength of the magnetic field. So this structure, the 2 ceramic ferrite magnets and a gap between them of approximately 15 millimeters, okay? The magnetic field strength there was 0.14 Tesla. And the force being experienced, the conductor so this conductor was passing through the gap, so it was placed right in the very center of the magnetic field. The conductor experienced an upwards force and the magnetic structure experienced a downwards force on the scale. So the forces were equal and opposite according to Newton's third law. And from that, we've been able to derive the fact that this magnet has a magnetic field strength of 0.14 Tesla. If we had used a stronger magnet, then the graph would have had a correspondingly higher slope. But I don't have access to strong magnets of that sort. But hopefully you've gained something from this. This is how to demonstrate the motor effect using a scale, a digital scale, a fixed magnet placed on the digital scale, and the conductor will push the magnet structure when you apply current to the conductor. Hopefully you've learned something from that. So I'll see you next time when we do another of our videos for the New South Wales High School Certificate Physics course. Bye for now.